question at hand concerns the appropriate sizing of a secondary breaker for a 75 kV step-down transformer, specifically stepping down from 480 volts to 120/208 volts Y. The transformer has a calculated full load amperage of 260 amps on the secondary side, and the proposal is to use a 225 amp breaker, despite the calculated full load amperage, citing that inrush current is not expected to be an issue, and further mentioning that the instantaneous setting can be adjusted to 10 times on the main breaker. The fundamental principle governing this scenario is that the secondary breaker should generally not exceed the transformer's full load amperage. In this instance, the transformer's full load amperage is calculated to be 260 amps, while the proposed secondary breaker is rated at 225 amps. This configuration would constitute a violation of the National Electrical Code, specifically Section 450.3b. The assertion that inrush currents are not anticipated to be problematic is not a sufficient justification for deviating from code-compliant breaker sizing. Inrush currents are inherently unpredictable and can occur unexpectedly due to various factors on the load side. Therefore, relying on an assumption about inrush current magnitude does not negate the need for proper overcurrent protection. Furthermore, adjusting the instantaneous setting to 10 times the breaker's rated amperage may not provide adequate protection against inrush currents. These currents can be exceedingly high and have the potential to damage the transformer if they are not cleared rapidly and effectively. It is of paramount importance to utilize a secondary breaker that is appropriately rated for the transformer's full load amperage. This practice serves to protect the transformer from potential damage and ensures its safe and reliable operation within the electrical system. To elaborate further, let's delve into the specifics of National Electrical Code Section 450.3b. This section addresses the overcurrent protection of transformers rated over 600 volts, nominal. While the question involves a transformer stepping down from 480 volts, understanding the principles outlined in 450.3b is crucial. This section dictates the maximum overcurrent protection settings for transformers based on their impedance and voltage rating. The primary purpose of overcurrent protection is to safeguard the transformer against overload and fault conditions. Overload conditions occur when the transformer is subjected to a current draw exceeding its rated capacity for an extended period. Fault conditions, on the other hand, are characterized by short circuits or ground faults that result in a rapid and substantial increase in current flow. In both cases, excessive current can lead to overheating of the transformer windings, insulation breakdown, and ultimately transformer failure. Therefore, it is essential to have overcurrent protection devices in place that can quickly interrupt the circuit under these abnormal conditions. The National Electrical Code provides specific guidelines for selecting the appropriate overcurrent protection device rating. These guidelines take into account the transformer's full load amperage, impedance, and voltage rating. The goal is to select an overcurrent protection device that will protect the transformer from damage without causing nuisance tripping under normal operating conditions. In the scenario presented, the proposed use of a 225 amp breaker on the secondary side of a transformer with a 260 amp full load amperage violates the fundamental principle of providing adequate overcurrent protection. The 225 amp breaker is undersized and would likely trip prematurely under normal operating conditions, especially during periods of high demand. This could result in frequent power outages and disruptions to the connected loads. Moreover, an undersized breaker may not provide sufficient protection against fault currents. Fault currents can be several times higher than the transformer's full load amperage, and an undersized breaker may not be able to interrupt the current quickly enough to prevent damage to the transformer. Inrush current, as mentioned earlier, is another critical consideration in transformer protection. When a transformer is initially energized, it can draw a large inrush current that is several times higher than its normal operating current. This inrush current is caused by the magnetization of the transformer core. The magnitude and duration of the inrush current depend on several factors, including the transformer size, impedance, and the point and the voltage waveform at which the transformer is energized. While it may be tempting to overlook inrush current considerations, It is important to recognize that inrush currents can damage the transformer if they are not properly managed. Repeated exposure to high inrush currents can weaken the transformer windings and insulation, leading to premature failure. To mitigate the effects of inrush current, it is common practice to use time delay fuses or circuit breakers with inverse time characteristics. These devices allow for a brief period of overload without tripping, which helps to accommodate the inrush current. However, it is important to select a time delay fuse or circuit breaker with an appropriate time delay characteristic to ensure that it will not trip under normal operating conditions. The adjustment of the instantaneous setting on the main breaker, as suggested, may not be an effective solution for protecting the transformer against inrush currents. The instantaneous setting is designed to provide rapid protection against high-magnitude fault currents. However, it may not be sensitive enough to detect and interrupt inrush currents, which are typically of low magnitude but longer duration. Therefore, relying solely on the instantaneous setting to protect against inrush current is not a recommended practice. In addition to selecting the appropriate overcurrent protection device, it is also important to ensure that the transformer is properly installed and maintained. This includes verifying that the transformer is adequately cooled, that all connections are tight, and that the insulation is in good condition. Regular inspections and maintenance can help to identify and address potential problems before they lead to transformer failure. To summarize, the proposed use of a 225 amp breaker on the secondary side of a 75 kilovolt-amps transformer with a 260 amp full load amperage violates the National Electrical Code and compromises the transformer's safety and reliability. It is essential to select a secondary breaker that is rated for the transformer's full load amperage to provide adequate overcurrent protection and to mitigate the effects of inrush current. Furthermore, proper installation and maintenance are crucial for ensuring the long-term performance of the transformer. Choosing a cheaper panel and main breaker is not worth the risk of damaging the transformer or violating the National Electrical Code. It is always best to err on the side of caution and to ensure that the electrical system is properly protected. Now let's discuss alternative solutions for achieving the desired cost savings while maintaining code compliance and ensuring adequate transformer protection. Firstly, it is important to re-evaluate the load calculations and determine if the connected load is truly as high as initially estimated. In some cases, the load may be overestimated, which can lead to the selection of an unnecessarily large transformer and associated overcurrent protection devices. If the load can be reduced, it may be possible to use a smaller transformer and a correspondingly smaller breaker. Secondly, consider using a transformer with a lower impedance. Transformers with lower impedance typically have lower inrush currents, which can make it easier to select an overcurrent protection device that will not nuisance trip. Thirdly, explore the possibility of using a different type of overcurrent protection device, such as a solid-state trip circuit breaker. Solid-state trip circuit breakers offer more precise and adjustable protection settings compared to traditional thermal magnetic circuit breakers. This can allow for a more optimized overcurrent protection scheme that provides better protection against both overload and fault currents. Fourthly, consult with a qualified electrical engineer. An electrical engineer can perform a detailed analysis of the electrical system and provide recommendations for the most appropriate overcurrent protection scheme. They can also help to ensure that the electrical system complies with all applicable codes and standards. Finally, consider the long-term cost of ownership. While a cheaper panel and main breaker may save money upfront, they may also lead to higher maintenance costs and a shorter lifespan for the transformer. A properly sized and protected transformer will typically provide more reliable service and last longer, which can result in lower overall costs in the long run. In conclusion, while cost savings are always a consideration, it is important to prioritize safety and code compliance when selecting overcurrent protection devices for transformers. The proposed use of a 225 amp breaker on the secondary side of a 75 kilovolt-amps transformer with the 260 amp full load amperage is not recommended and should be avoided. Instead, explore alternative solutions that will provide adequate overcurrent protection and ensure the safe and reliable operation of the transformer. Remember, electrical safety should always be the top priority. It's not just about saving money, it's about protecting people and property from harm. An adequately sized breaker, in accordance with the National Electrical Code, is a critical component of a safe and reliable electrical system. By adhering to these guidelines, you can ensure that your electrical system operates safely and efficiently for years to come. Moreover, let's think about the implications of a transformer failure. A transformer failure can result in significant downtime, lost production, and costly repairs. In some cases, a transformer failure can even lead to a fire or explosion, which can have devastating consequences. Therefore, it is essential to take all necessary precautions to protect the transformer from damage and to prevent a failure from occurring. Proper overcurrent protection is one of the most important safeguards against transformer failure. By selecting the appropriate overcurrent protection device and ensuring that it is properly installed and maintained, you can significantly reduce the risk of transformer failure and its associated consequences. In addition to overcurrent protection, it is also important to consider other factors that can contribute to transformer failure, such as overheating, insulation breakdown, and contamination. Overheating can be caused by overloading the transformer, inadequate cooling, or poor ventilation. Insulation breakdown can be caused by age, moisture, or voltage surges. Contamination can be caused by dirt, dust, or other foreign materials. To prevent these problems, it is important to ensure that the transformer is properly installed, maintained, and operated within its rated capacity. Regular inspections and maintenance can help to identify and address potential problems before they lead to transformer failure. Furthermore, consider the impact on insurance coverage. Many insurance companies require that electrical systems comply with the National Electrical Code in order to be covered in the event of a loss. If an electrical system is found to be in violation of the National Electrical Code, the insurance company may deny coverage, leaving the owner responsible for all costs associated with the loss. Therefore, it is important to ensure that all electrical work is performed by qualified professionals and that it complies with all applicable codes and standards. This will help to protect your property and ensure that you are adequately covered in the event of a loss. In addition to the financial implications, there are also ethical considerations to keep in mind. As an electrical professional, you have a responsibility to ensure that the electrical systems you design, install, and maintain are safe and reliable. Cutting corners or compromising on safety in order to save money is unethical and can have serious consequences. It is important to always put safety first and to adhere to the highest standards of professionalism. Remember, your reputation is on the line. By providing safe and reliable electrical services, you can build a strong reputation and earn the trust of your clients. This will lead to more business and a more successful career. Now, regarding the statement that the instantaneous setting can be set to 10 times on the main, remember that the instantaneous trip setting is designed to provide very fast protection against high-level fault currents, typically short circuits. While it can help protect the transformer, relying solely on this setting for transformer protection is not advisable for several reasons. Firstly, the instantaneous setting may not be sensitive enough to detect lower-level overloads that can still damage the transformer over time. Secondly, setting the instantaneous trip too high can reduce the overall coordination of the electrical system, potentially causing other protective devices to trip unnecessarily. Thirdly, as previously mentioned, the instantaneous setting is not specifically designed to address inrush current. Inrush current, while not a fault, can still stress the transformer and other components in the circuit. Therefore, a more comprehensive approach to transformer protection is necessary, involving properly sized overcurrent devices and potentially specialized transformer protection relays. Also consider the role of upstream protection. While the focus is on the secondary breaker, the primary side protection is equally important. The primary side overcurrent device should be coordinated with the secondary side device to ensure that faults are cleared in a selective manner. This means that the device closest to the fault should trip first, minimizing the impact on the rest of the electrical system. Coordination studies are often performed to determine the appropriate settings for all protective devices in the system. These studies take into account the transformer's characteristics, the connected loads, and the potential fault currents at various points in the system. The results of the coordination study are then used to select and set the protective devices to ensure optimal performance. In conclusion, the decision regarding the secondary breaker size for a transformer is not simply a matter of cost. It is a critical engineering decision that must take into account safety, code compliance, and the long-term reliability of the electrical system. By understanding the principles of transformer protection and following the guidelines of the National Electrical Code, you can ensure that your electrical system operates safely and efficiently for years to come. Finally, never underestimate the value of professional training and continuing education. The electrical industry is constantly evolving, with new technologies and new codes being introduced on a regular basis. It is important to stay up to date on the latest developments in order to provide the best possible service to your clients. There are many resources available for electrical professionals, including seminars, workshops, online courses, and trade publications. Take advantage of these resources to enhance your knowledge and skills and to stay ahead of the curve. Remember, investing in your education is an investment in your future.